The crew itself, so this was the mechanical interface, the crew itself will see that. So the crew interface is one screen which is giving you all the joint angles and the different modes and the different alarms and what you want to do. So this is the very first screen. The other one, the crew interface, is a hardware display. It's a hardware control panel where you can command the cameras, you can command in the which joints you want to select, and in the brakes, and as well as the emergency stop. So this is a hard panel that we have seen in the cupola, this black box. And then the other interface is, as I explained before, are your free screens on the top one. In the free screens, you add on top of that overlays giving you your speed, your joint angles, as well as some of the mechanical indicators and telemetry on the screen. When you fly the arm, as I said, we teach during basic training, it's not only how to use this interface and how the mechanical interface is built, but also the mental math you need to do when you fly the arm, how you actually manipulate that. So in robotics, we use 4 different coordinate systems. The frame of resolution is the frame which is at the end of the arm. So this is the thing that you are really flying. The display frame is the frame that gives you in which coordinates the values that you see are referenced in this display frame. How you command this arm, you can decide to fly in the arm like you fly an airplane from the inside, but you can also decide to fly the arm from the outside, like if you will land an airplane from the tower, and that would be an external command frame. And to convey your commands to the arm, you will have the hand controller frames, which are the frames attached to joysticks. But when you fly the arm, sometimes the arm can get into configuration where it loses a degree of freedom. So losing a degree of freedom is like if you extend your arm and suddenly you cannot go further than that. You cannot go further in one direction. That would be a singularity. Some of the singularity is also for you, you can lock your elbow or you can lock your wrist in a certain configuration that don't allow you to go further pitching down. The SSRMS has 7 degrees of freedom and it has 5 singularities. And sometimes we can even lock one joint on purpose and it has 5 more singularities. All that, when we do training, the crew has to avoid being in the singularities. Any singularities will make the arm lose 1 or more degrees of freedom. Also, during training and during flight, the crew and the ground has to avoid any collision. Of course, we mitigate this kind of collisions by doing a good planning and having the proper camera view. So if you have always a good camera view, you will know that you are colliding or not. And either you have collision with structure, so you move your arm too close to any kind of structure, but also the arm can auto-collide with itself. It's like if you are scratching your shoulder, that's an auto-collision, actually. And we try also to mitigate that using camera views, planning, but also there are some software part in the arm that tells you, hey, your hand is getting closer to your shoulder, you have to watch out. That's what is shown here on this display. We have like charts helping us to avoid these collisions. Other limits that we have when we fly the arm is we have to avoid these obstacles, so going around antennas, cameras, or trusses or structure. Also, all the joints has a certain limit. They cannot spin forever, so they are limited in plus minus 270 degrees. And also, another operational limit is when you fly the arm, you have a certain set of cameras. You don't have an infinite number of cameras, and sometimes the camera view is not the best you have to do what you want to do. So it's a limiting factor of where the camera is, how the camera can pan, tilt, and sometimes the camera contrast and quality is not very, very good, so you don't really see. So the ground as well as the crew are trained to mitigate these kind of things and to make use to what you have. And also the illumination. So here you have a picture of Terry Wirtz flying the arm, and he was in the cupola, and you see that the sun in your face is of course not really helping a lot because you can blind you. And the arm is sometimes also restricted to how big the payload and how bulky the payload is. And we saw at the beginning a video how the biggest space station module, the GEM, was installed on the station, and this is a limiting factor, and also how fast the arm can move. Because if you want to grab a visiting vehicle that is drifting away and you are not fast enough, then you cannot detach the arm to run after it. Part 5, and that's the last part of this lecture, is we will try to improve these robotic assets. And one improvement is to finally get something on the Russian side, to have robotic aspect on the Russian segment, and this is ERA, which is still on the ground. ERA is a long-standing European project, partnership with the Russians, and you can see the details of ERA. I will not detail it too much, but this will enlarge the robotic assets with some different interface. We will not fly ERA in the cupola or in the US lab. It will be mostly flown by ground or during EVA. But okay, ERA is a little bit in a tricky situation right now where it's still on the ground and we are still waiting for a flight. Something we try to enhance, you have seen we have hand controllers, but the crew doesn't really feel what they do. We try to enhance that by having a better robotic assets by having a feedback, force feedback on one of the joysticks. And this is the purpose of one of the ESA projects, to have interact where the crew feels, so they are driving a little robot on the ground and the robot has an arm. And for instance here, Andreas Morgensen was trying to align a pin held by the robot in a hole, and he could feel the border of the wall using force feedback on the joysticks, as you can see. Also, we were trying to test teleoperation so that the crew was also driving a little rover on the ground. So here there is a mock-up of ExoMars rover, which is supposed to take off to Mars in 2020. And one of this engineering model was driven by Team Peak from the station using different interface, no joystick, but more laptop interface to drive the rover around it. Also, Subfish Justin was an interesting experiment to enhance this force feedback, where we tested new ways of commanding from the station. And here you see a very short video of how this robot was actually flown a few weeks ago by Paolo Nespoli, where Paolo was actually commanding the robot from the station, and the robot was able to automatically himself take a tool and repair a faulty solar panel and then change different operation modes. So this was a kind of semi-autonomous robot supervised by the crew. It's also these new ways of new approach and robotics we do. It's also, as you see, a bunch of young people here in the Belgium Control Center. It's also very nice, this operation, not only to test robots and test new protocols, automation and new mechanical interface, but it's also for us to test new ways of how people are new centers. For instance, this is most of the robotic assets, as I said, are in Houston or in Canada. And in Europe, we are developing with young teams new ways to control the arm from the ground. And one of the coming up next project we have is, instead of having only one joystick with force feedback, the crew will actually not just hold the joystick, but having a full exoskeleton 3D printed, and they will operate, they can feel completely what the arm is doing, either in the station or a robot on the ground or on another planet, and they can really feel using the exoskeleton. So, summary, what we have seen today, we have seen different elements of ISS robotics. As of today, SSRMS, SPDM, the mobile base that allows the SSRMS to go about everywhere on the station, and the GEM-RMS, the Japanese robotic arm. We have seen that the functions are very large. One of the key is to support visiting vehicle, but also EVA, but also repair inspection. We have seen that we are limited to a certain place where your payload can go, and then when the arm can put your payload. Again, when you have a visiting vehicle, you can berth only in 2 ports. How to operate the arm, we have seen that we have cameras, we have control panels, we have mechanical interface being SSRMS or SPDM, and you are limited to this kind of interface. And how the ground is doing it, it's also a different story. I didn't detail it too much, but the ground has more than these tools available. And we have seen also at the last part of this lesson that the ISS is used as a testbed for new robotic assets for the station, but also for future exploration, like planetary exploration, like Mars or the Moon. Thank you very much for your attention, and I wish you a very good day.